one lecture today and another one tomorrow. And I would like to start with a small quiz. I'll show you some images or movies, and you have to guess what the model is. First one. Anyone knows what this is? Lawrence? Any other proposition? Next. Harder. Any idea? Hmm?
Increasing the temperature in a phase separation problem.
This one, easier.
Isn't that predator-prey? Okay.
This one. Random motion. Anything else? Doesn't look like a wolf trajectory. Look closely. VCheck model, great. Last one. The same model with neighborhood interference. Okay. I just showed you 6 models, I think. Oh, no, there's a last one, this one. What? Forced population. Great. So I got some answers, and on my end, I have no idea. Because, well, I just from qualitative observations, I cannot guess a model. Actually, you need some quantitative analysis in order to get a model. You can say, okay, this looks like a forced population. This looks like a VCheck model. But if saying that it is this model, it's a very strong assertion, right? It's a very strong statement. You're saying that, well, there are parameters of the model, for instance, the VCheck model, for which you would reproduce exactly all the statistics of this data. Big claim. I cannot do this by eye. And that's going to be essentially the main focus of these 2 lectures. I would like to teach you and to show you how you can learn model from data, in particular in the case of the dynamics of patterns forming systems, like the ones I've shown you. And throughout the lectures, we're going to get back to each of these 6 examples and actually learn the model by analyzing the data I've shown. Or learn a good model. Maybe it's not going to be the right model. Okay, so basically the game we've been playing so far, we were on this side of the screen, on the theoretical physics side, looking at the side which makes theories of pattern formation, looking at the other side, and proposing models. Models are, well, equations that instantiate the theories that we've been developing, stochastic dynamics, reaction diffusion, critical phenomena, and so on. And these equations, if we just do theory, we can only hope that it will describe, to some extent, the pattern-forming systems that we're interested in, from bacteria, proteins inside bacteria, predator-prey models, ecosystems, groups of animals, etc., etc. I think you have a good idea of the range of systems that we can study in biophysics. So at this stage, this is what Nigel would say, would call getting something from nothing. We have no data, we just have an idea of what's going on the other side. We can use symmetries, we can use arguments and propose models. Great, but how do we get closer to reality? Well, we need to send the experimentalists to the other side. And what will they do? They'll acquire data on, if you're interested in the dynamics of pattern-forming systems, I guess they're going to take movies. And these movies will now give us something to compare with. It will give us, and will allow us to do qualitative comparison between the prediction of our model and the experimental data. That's nice, that's qualitative. We can adjust the parameters so that it looks the same, so that, for instance, it looks like it's the same universality class. But it's still a big leap of faith, right? Then if you want to do a bit more, and that's the most classic approach, you're trying to get quantitative. And for that, you need to analyze your movies. And typically, for instance, if you're looking at birds or at bacteria, you can track them and obtain trajectories. In other cases, you can filter it to get concentration fields. You can analyze your time series to get population abundances. And that will give you trajectories. The trajectories are the traces in space-time of your experimental object, of your system. And you can analyze them quantitatively now. For instance, you can look at correlation functions. You can look at densities. You can look at, basically with the correlation functions and the different moments, you get everything. And now you can fit your model, fit your equations to adjust the parameters such that it reproduces quantitatively these correlation functions. And if you're lucky and if you started with the right class of model, you can get something that does very well. So just using your brain and adjusting a few aggregate observables, you can get good models for your data. But there's still a small leap of faith here, which is that you've thrown away most of the data. You're only using a few aggregate observables, these correlation functions, for instance, and most of the data is left out. So the goal of these lectures is to finish bridging this gap and study inference methods that will directly connect the raw trajectories to quantitative models. Try not only to fit the data with a model, but also to learn the functional form of this model, to compare different models, to select the models, to discover mechanisms, and hopefully new physics in these experimental data. Any questions so far? Okay, so this is a big problem, and what we'll be playing with as input, our main player, will be trajectories. These trajectories can look many different ways. What comes to mind maybe first, at least to someone who hasn't taken 10 days of biophysics courses, is these nice orbits of planets around the sun, or these nice regular harmonic oscillators, etc., that are well modeled by ordinary differential equations, such as Newton's second law. Now, these trajectories have a key property, which is that they're deterministic. If you take all the planets and set them again with the same initial speed and the same initial position, for a long time, the trajectories will look exactly the same. And so that's basically a big difference with experimental systems in biology. If you take proteins inside a cell, if you take bacteria inside a petri dish, a C. elegans swarm, a group of animals, even an ecosystem, and you make the initial condition as close as possible. You make 2 experiments with initial conditions as close as you can. Very, very quickly, they will start looking very different, actually from the start for these systems. And the reason for that is that the dynamics is non-deterministic. It is stochastic. It's stochastic because of many different sources of stochasticity. We've heard about a few last week. I think the most fundamental one at the level of classical physics is Brownian motion, which you get from the thermal noise. So that's basically the baseline. In order to remove the Brownian motion, you'd need to freeze your sample down to the absolute zero. So that's rarely an option with biological systems. And so you always have this baseline of noise. Now, if you go up in scale, it matters less and less. For micrometer scale objects, you can still see it. At the tens of microns and hundreds of microns scale, basically, at relevant time scales, it's very rare that you can observe Brownian motion. But at larger scales, you have other effects that emerge. In particular, active fluctuations. So you don't only have Brownian agitation in cells and in living systems. You also have all the enzymatic activity, the molecular motor activity, all the proteins being synthesized and degraded, the loop extrusion inside the nucleus that generates motion at large scales, et cetera, et cetera. All of this creates some directed motion for some processes and a lot of noise for the rest. It's a big molecular pogo where the molecules just shake each other. And that does not go down so fast in scale, but it still goes down when you increase the scale. But now if you go to the organism scale and above, then you're starting to have something else that emerges, which is inner complexity of these systems. Essentially, no matter how many degrees of freedom you track, whether you track just the position of the worm, its shape, or even the states of most of its neurons, you're going to have a huge hidden complexity in these systems that you're not going to be able to include in your models. And this, to you as an ignorant observer, not knowing what these states are, will look awfully like random motion, some level of random motion. Not only random, of course, there's also like deterministic parts, but the part that you don't know will look random. And for all this, there's a pretty unified framework that works for many, many different systems, which is called stochastic differential equations. Basically, the easiest way to get to them is to just look at Newton's second law and add a noise term here. This psi of t will model, for instance, the random shocks with water molecules and so on. Maybe a simpler version that is more useful and more generally applied is the overdamped limit. So you know that if you're in viscous fluid and you're at very small scales, your Reynolds number goes down, inertia effectively vanishes, and so you have essentially an instantaneous balance between the forces, the thermal forces, and the deterministic forces that include the damping, the friction. That leads to this model, which I will call Brownian dynamics, dx over dt, where x is the state of your system. So it can be the position of one molecule, of many different bacteria, of a flock of birds. It's a d-dimensional vector that describes your dynamics. The dx over dt equals a sum of two parts, a part that I will call the force, that is also called drift, and a random part that what was that? Never seen this screen before, okay. And a random part that will be characterized by the magnitude of its stochastic amplitude, or that we also call D, the diffusion matrix. It can be a scalar, it can be a matrix, but that's the main point. I will get back to this equation, of course, more formally when we get to the blackboard. But for now, I would like to show you what the main goal of these lectures is going to be. The goal is to infer stochastic or non-stochastic differential equations from data. So your input is going to be the trajectories that I showed earlier. Experimental trajectories of positions, orientations, shapes, abundances of populations, concentrations, possibly fields of concentrations. And it's going to be a discrete time series at discrete times, hopefully not too far away from each other in time, otherwise you're going to be in trouble. But we'll get back to this. And the goal is going to be to reconstruct that kind of dynamics. dx over dt equals a deterministic force plus possibly a random noise. So that's, yeah, this arrow here is the main question of these lectures. And it's a very important problem at many different scales. We've already discussed about the dynamics of living systems. Hey, maybe that would be a good model for fish schooling. I don't know. But it's also very broadly used in other fields, such as colloidal dynamics, soft matter, active matter, of course, where this is actually a very, very good model. Neural dynamics, neuroscience. If you look at electroencephalograms, they look pretty noisy, and they can be modeled by this kind of equations. Finance. Brownian motion was actually, I believe, invented for finance first. Brownian motion. The Wiener process, the mathematical formalism, was derived for finance. Climate dynamics, population dynamics, epidemic spreading. All of these fields use stochastic differential equations to model the dynamics of the observables. With different, and in all of these fields, it's important and desirable to be able to learn these dynamics from the data for different purposes. In these systems, I would say that the goal is to characterize mechanisms, to try to understand, for instance, the interaction between proteins in a protein network, the social interaction between fish, the alignment between colloidal particles. This can also be used as a diagnostic tool. How do we distinguish highly random electroencephalograms, for instance, well, maybe by getting a model for these complex EEGs. In finance, global warming, and epidemic spreading, I guess there's a pretty different general goal, which is making predictions in the future, which is not really what I'm going to talk about in these lectures, but it's also very useful to have quantitative understanding of these systems. Okay, very broad, lots of possible applications. So why hasn't this all been solved a long time ago? Well, it's because it's a difficult problem that we're nowhere to be able to call solved, but we're making progress in it. There's been progress on it for decades, but it's been really accelerating in the past few years. I would say in the past 10 years. The main difficulties we're facing is that it's already a pretty hard problem if you have perfect data. This is perfect data. This is a very, very long, infinite time series of very, very close by points with infinite resolution. That's not what you get when you do biophysical experiments. There are challenges typically specific to biophysical experiments, which are, for instance, that your trajectories tend to be short. There's a finite total time to it because your molecules are going to bleach out or degrade. Your cells are going to divide, die. Your birds will fly away or just stop doing what they were doing. Your ecosystems, well, you can only observe them for so long, and then the PhD ends and needs to be defended. So there's always only finite amount of data, and for the same reason, there's always only a finite amount of time between data points. There's a finite sampling interval. If you look at systems at the molecular scale, the more pictures you take, the more you illuminate and degrade your system. And so there's a trade-off in resolution to take into account. If you look at larger scale data, for instance, population dynamics over years, I don't know why, but there tends to be five points of data, and then 2 points missing, and then 5 points of data, and then 2 points missing. Maybe the PhD students wasn't working on the weekend, etc., etc. Then you have a finite measurement error. You don't have a perfect representation of your data at all given points. Your measurement apparatus is always going to induce a level of noise that adds up and prevents from having a completely faithful representation of your data set. And really, I want to emphasize that this is different from the dynamical noise. We had this psi of t in the dynamics. This psi of t acts on dx over dt. So it's intrinsic to the dynamics, and it's integrated over time. The psi at time t will affect the dynamics forever after, with decaying influence, but it will change the state of the system. The measurement error comes from the measurement apparatus. It's like photon shot noise, blurring, resolution error, tracking mistakes, etc. That will lead to extrinsic noise on x of t, not on dx over dt. So of course, it's amplified if you differentiate your experimental system. If you differentiate a noisy signal, it gets more noisy. That's quite easy to see. And that one is an enemy. That one we want to just filter out. And last but not least, so far I've shown you a one-dimensional system represented by a one-dimensional data set. But actually, most often, you don't see the whole system. There's a bunch of hidden degrees of freedom that affect the dynamics, that really matter for your system, that couple with it, and that you don't have access to. For instance, because these degrees of freedom are out of the field of view, out of the focal plane, not fluorescently labeled, or maybe you just don't know what they are. Maybe there are parts of your system that you haven't characterized yet and that still have a major influence on your data. And so all you have to reconstruct your data set, your dynamics from data, are these short, sparse, noisy, partial data sets. And now that's a hard problem. I hope you can believe it. And this looks extreme, but actually, for instance, in cell migration data, that's a pretty reasonable data set. And there's something that can be extracted from it. Questions so far? Yes.
So you have the model that you mentioned first, which is a stochastic differential equation. But I was wondering that, let's say for some models, like V-check model, for example, you cannot write it in form of a differential equation like this one you wrote, right? So I was wondering, for this type of model, how can you inference? It's highly dependent on the model that you suppose, like what you...
That is true. So the V-check model, I would call a funny model. Funny because it has, depending on its implementation, discrete times. Yeah. A pretty arbitrary rule where you replace one orientation with the local average, and a hard threshold in space. I don't know any physical system that has that kind of features, right? Yeah. It's a beautiful model to do theory, to get something from nothing. It's a beautiful model if you want to stay on that end of the bridge. Mm-hmm. But if you want to relate to data, that's just not a great starting point, because it shows these discontinuities, these arbitrary things that are not easily tuned, right? So you can write stochastic differential equations with alignment terms that will depend on distance, for instance, smoothly. That can depend also smoothly on the number of neighbors around. That can depend, and then that will have noise. You will not reorient immediately, but you will rotate. You will have a torque. And then you can try to fit all of these to the data and get that as close as you can. And this is actually what we're going to try to do with one of the data sets that I showed earlier.
Okay, thank you.
But not all models are made to be fitted on data. Some are just great to study universality classes, but they're mostly there in the brain of theoretical physicists.
So it's like the V-check model is too much discontinuous.
Well, the V-check model is a beautiful idea from 1995 that has been very much overstudied, and that has many variants that are much more realistic, I would say. Other questions? Okay. So that's the plan of these lectures. I think for today, we'll mostly stick to deterministic dynamics. I would like to give you just a primer on how to fit naively a dynamical equation on data. Then I will discuss two recent developments in the field in France. This CINDI is sparse identification of nonlinear dynamics. It's a big paper from about 10 years ago. And physics-informed neural nets are even more recent, and they're getting traction and very, very hot these days. None of them has been extensively applied to biophysical systems, but I'm showing them because, well, first they could, provided that you have a deterministic enough system. And I also think it will help a lot understanding what's going on in the stochastic case. Then the second part of the lectures, which will mostly be tomorrow, we'll see how far we get today, will be on stochastic dynamics, and it will be more closely related to my research and the research in my group. And I will show how, well, I will first get a recap on stochastic differential equations, because I think there's some useful things that need to be said. And then I will show how to fit, how to compare, and how to discover stochastic differential equations. Let's go. This is intentional. Learning deterministic dynamics. So we're going to start with the simplest deterministic dynamics, which is just a first-order differential equation. dx over dt equals f of x. And I will loosely call this f a force. Yeah, it does not really have the dimension of a force. It has the dimension of a velocity, but it's the, yes. I will call it a force. The question is how, from a trajectory, xt, x t0, t0 plus delta t, x t0 plus n delta t, how can we learn this force field? So this force that depends on your variable x. And I'm making actually a pretty critical assumption here. So this is x at time t. I will write it as an index like this. I'm making the assumption that your dynamics is autonomous, meaning that the force only depends on the state, xt. X here can be a d-dimensional vector. I'm not going to care too much about vector notations or indices. They're of course, in the papers that, that we relate to, but it would just make all the notations more heavy without having much physics added to it. So how do we do that? Well, so the goal is to get f hat of x, an inferred force field that approximates f as well as possible. This is an optimization problem. And like any optimization problem, basically, we'll want to define a loss function that will be 0 if you get the perfect answer, and non-zero or larger, and that will grow if you're with the error that you're making. But to do that, you need to know what to put in your loss function, how to compare your inferred force with the true force. And for that, and you don't have access to the true force from the data, but you have access to dx over dt. So the key ID that we'll use, the basic ID, is that the position increments, the state increments, delta xt, which I define as xt plus delta t minus xt. This is f of xt times delta t plus O of delta t squared. And now if we assume that delta t is small enough, we're just going to neglect this part and say, OK, to get f of xt, I will try to minimize the discrepancy between my inferred force and my differentiated system, my differentiated state, delta x over delta t. So my loss function is going to be proportional to these differences. Now, how do we do that in practice? Well, we first need to specify a functional form for this for this inferred force. So in which space of functions are we going to look for this inferred force field? And that's a crucial question, because if you just say the whole space of functions, it's far too big. It's far too big, really not structured enough to just fish one function in the whole space of function. You need some regularization. You need some way to make it lower dimensional. And there's different ways of doing that. Basically, we can distinguish parametric approaches, where you come up with a model that has parameters and you try to optimize these parameters, and non-parametric approaches, which basically are also parametric, but the parameters are more generically proposed rather than coming from a proposition from the users. So, and then there's two more questions that one more choice that you have to make. It's whether you're linear or non-linear in these parameters. not in the function, in the parameters. We'll see what this means in a second. So in the parametric case, so this will look, for instance, like an f of x theta, and theta is going to be your parameter. So if you optimize the theta, you will get a f hat of x. Your inferred force equals your general function at a value theta hat that minimizes your loss function. Theta hat is the argument of the minimum over theta of the loss function that is a function of theta. We'll get back to this in a second. Now, there's a simplification of this that you can make, which is if your function f here is a linear combination of known functions, and the thetas are just the prefactors. So this will be and examples of this include polynomials, for instance, Fourier modes. And that's, for instance, when you want to do a simple Taylor expansion of your force field and learn the coefficients of the Taylor expansion, that's going to be a very useful approach. It's very generic, very basic. That's the one that requires the least math. And so it's useful. Then we can move to non-parametric systems, and that's going to be the second part of this lecture. The non-parametric cases in the linear case is basically starting not with a basis of your choice, like polynomials or a small basis, but a huge basis with a lot of candidate terms, and then removing as many of them as possible. And you don't know in advance which ones will be removed. And this is, for instance, what CIND does. And finally, the case of non-parametric inference with nonlinearities in the parameters is, for instance, the case of neural nets. There's also a slightly less popular these days class of approaches that still is very powerful, which is called kernel methods. And which I just mentioned because it's good to know it exists. So now I would like to take this lecture plan. Start with nonlinear parametric, go to linear parametric, then non-parametric linear, non-parametric nonlinear. That's the plan. Questions? Okay, yeah. No, not yet. Again in this lecture, yes. It's not very important. It's not very important. I can do this lecture without using the projector anymore. I'm happy I got this already. Okay. So in order to do the nonlinear parametric inference, what we need to define is this loss function. And we already have a good start because we know where in the data we can find something that looks like what we want. We know that if you look at delta xt, which is computable with the data, you get an approximation of f of xt. So let's try to use it. If we define the loss function L of theta as, so we're going to take a parametric form. This can be any model that depends on the parameters in any way. As an example, for instance, you can say that f of x, f of x theta can be, I don't know, minus x theta 1 e to the minus x theta 2 plus etc., etc. You can, this is a linear, there's a linear dependence in this parameter, a non-linear dependence in this parameter. And this kind of form can come from earlier modeling. We've seen a lot of such forms, for instance, in the population dynamics systems, where you had dynamics that had, what was it called? This xi over xi plus h kind of term. It's the functional response, yes. Thanks, Ricardo. This h is a nonlinear parameter that you would want to adjust on the data. Okay, so your loss function in the in theta is going to be a sum over all time points of the discrepancy between your predicted force and the observed force. Delta xt over delta t minus f of xt theta. You want f to minimize the distance to delta x over delta t. So a very common approach, that is the analytically easiest one, is just to do least squares. This, if you minimize it, and if there's a perfect solution, meaning if you can completely fit f of xt, so this is non-negative, of course, it's a sum of squares. It's 0 if you perfectly fit delta x over delta t with f of x theta. And then, so you can put in a minimizer, so for instance, conjugate gradients or BFGS are good minimizers for nonlinear problems. There are implementations in Python of these. Don't go coding your own minimizers. This is a full-time job. I mean, you can try, but it's a job. Then if you minimize this, you'll get the optimal value for theta hat. Theta hat equal arg min over theta of L of theta. That's the one that best explains the data. Based on this approximation, based on short time increments and fitting the short time increments with the force field. Now, an interesting and important point is that you're not constraining at all about the long-term dynamics. If you do a good fit, if your inference works, it will predict also the long-term dynamics. But we're really trying to capture the short-term part of the stochastic differential equation. So that's a general recipe for nonlinear fitting, for the nonlinear parametric inference. And I cannot say much more than that on the blackboard, because then the next steps is to use a numerical solver, essentially. However, there's a specific case where I can go much further, which is the case when the dependence of the force field on all your parameters is linear. More specifically, if you take a basis function, so we're going to decompose our force field on the basis of known functions. We're going to take a basis, I can call it B, of functions bi of x, I equals 1 to nb, that you're going to propose. I mean, this can be a systematic exponential. A systematic expansion in terms of polynomial functions, for instance. So if you have a 2D system in x and y, these functions bi of x can be 1, x, y, x squared, xy, y squared, and you stop at a finite order. You can also use sines, cosines, exponentials, and such. The important part is that you depend, for sines and cosines, for instance, the phase, so the wave number is not going to be a parameter, it's going to be known. So for instance, if you have a known box size, you can make a Fourier expansion over this, because this L here is going to be known, and you're going to use sine 2k pi over L with k varying discretely. But if you have to adjust this L2, then you're out of the linear regime. And everything gets a bit more complicated. But if you, okay, so that's the, and then what we're going to write is that we're going to replace our f of x theta by a linear combination sum over I of the fi coefficients bi of x. So these are known, and these are the coefficients to infer. Okay, this is actually pretty easy to solve analytically. The loss function L now depends on the fi, and you can write it as the sum over t. So I'm going to replace this by a time average of the square up. Let me add 1 over n delta t here. It's just a proportionality factor, but that will make everything a bit nicer later. Anyway, minimizing 1 over n delta t, that, or minimizing that is the same. Okay, so this, this loss function now is the time average, and to be formal, I will add a delta t here, so that it looks like an integral in a continuous limit. And this is really a time average. Okay, so this is the time average of delta x over delta t squared plus, minus 2 sum over I of the fi bi of xt delta x over delta t plus sum over ij of the fi fj bi of xt bj of xt. I've just expanded my square. Now, I want to minimize the loss function. So I'm going to write dl over dfi equals 0. This part disappears because it doesn't depend on the parameters. This one gives us minus 2 average bi of xt delta x over delta t. And this part gives us plus 2, because fi can be either of the two terms here, average sum over j, sorry, of the average of bi of xt, bj of xt. All of these being time averages. Now, so here, we've differentiated with respect to fi. So I is an explicit index, and j is a summed index. This is a linear system. We're going to define a matrix. Can you see if I write down? Yeah. We're going to define a matrix Bij as the average of Bi of xt, Bj of xt. And then this gives us a linear system. This is -2 times this. OK, wait, I need an fj, of course, here. Important. So what it gives us is that this is the vector f times the matrix B equals the vector B times delta x over delta t. We're going to invert this, and that gives us fi hat equals a sum over j of the matrix B inverse with indices ij times the time average of delta x over delta t bj of xt over time. Do you see it? I mean, is it clear? OK, so that's actually a pretty nice equation. You can implement it directly on your laptop in a few minutes. You just need to compute two averages, this matrix, which is basically the covariance matrix or the correlation matrix of your fit functions, and then the correlation between B and delta x over delta t. You invert this big B. If this is too large a matrix or if it's not invertible, you use a pseudo-inverse. And you do this dot product between this inverse B and delta x over delta t and this vector. And yay, you have reconstructed your force coefficients, fi hat. And now you can extrapolate your force field. You can evaluate it along the trajectory as f hat of x. The inferred force at position x equals just a sum over I of the fi hat bi of x. Question? Yes.
So I was wondering, how many polynomials do you choose in a real data?
This is precisely the next point.
Ah, OK. All right.
So far, we were looking at a linear parametric combination, meaning I give you the job as the user of the method to choose all your functions. I'm not going to give you a prescription of how to do this. I'll assume that you have a good model which is written as a linear, a good proposition that is written as a linear combination. Of course, it's a great question, and it's hard to find a general answer to this. Too many functions, and you'll overfit. And in particular, if you have any level of noise on your data, you're going to start fitting the noise too, and you'll get less and less extrapolation power. Too few functions, and you're not going to get a good fit because you're not going to have sufficient representation power to capture well a complex model. So this balance between overfitting and underfitting sometimes called the bias variance trade-off. So as a function of the number of parameters, if you look at the inference error, if you have too many parameters, you're going to overfit. Too few parameters, and you underfit. And then there's the sweet spot, which is just right. That doesn't mean that it's doing a great fit. It just means it's the best you can do with this data and this family of functions, because sometimes changing the type of functions, you can do a better job with fewer parameters. We'll talk a lot about all this tomorrow. One thing, maybe I can give an illustration. So if this is your data, if you're in the overfitting regime, you'll just try to go through all the data points, and that's going to lead to weird oscillation and an increase of the error. And anyone who's tried to do a fit with many parameters has experience with that. Underfitting is also nasty. For instance, if that's my data set, and I'm trying to fit this with a parabola, well, this is flatter than a parabola here, and there's no way a parabola can capture all of this. And I'll get some systematic errors that will prevent you from quantitatively capturing your data. Basically, so far, with parametric approaches, we don't really get a prescription for how to do this. What we're getting is the best in the function class. So that leads me to the next part, non-parametric approaches. David.
Whenever the data it's too sparse in time, I am thinking that maybe the order delta t squared may become relevant. Although I am a bit skeptic, but can happen. Do you know of an example where that could happen?
Pretty much all data sets in biophysics. I've very, very rarely seen data where the delta t was very small. Joao is working on data where there's a very small delta t in some cilium dynamics, for instance. That's rare. Generally, you barely have any correlation between subsequent points. And if you manage to infer a model, you're at the edge of what the methods can do. And so that's a major challenge for future works. Here, I've only presented you the most basic version of the fitting. Of course, you can be smarter. One thing you can do that will already help quite a bit is to take a fit at the midpoint here. This will kill a first order in the error. But you need to be careful with it. Then there are other tricks that you can do at higher orders. You can try to expand this in your loss function directly. Yeah. There are also techniques called data augmentation, which consist in essentially adding points, hidden points in the middle, that are, I think, an active research subject, basically.
Thank you.
Yes.
Yeah, I just had a quick question. So, of course, like picking the loss function is like a little bit of an art, right? Like it's, And especially, I always wonder with these, like, even limited to these, like, even power loss functions, like, is there, like, a intuitive way to think about, like how these, like, your solution would change? Let's say you made it to, like, the fourth power. Of course, you get, like, a nonlinear equation. But in principle, let's say you solve it, but that's not going to be the same answer as this, even though, in principle, you're trying to minimize the same thing.
Yes. So that's a good question. As soon as you deviate from this, from this least square method, essentially any analytics is hard. The idea is basically, if you change this loss function, if you have a perfect fit, you're going to get the same answer. But the way you deviate from the perfect fit will vary. For instance, if you replace this by power 4, how do you think this will change the fit? So that's my best fit with least squares.
I guess it'll have a larger penalty for things much further away, but I guess a smaller penalty for things really close.
Exactly.
Like small deviations, yeah.
So it will try to avoid large discrepancies because the fourth power will put the emphasis on the larger deviations, and so it will give a different answer.
Right.
And
so I guess like
which one is the best is
right, a priori is hard to say. Okay.
Yes.
Thank you. Yeah.
I mean, in systems of ODEs, I guess the question is whether it will be the best to. I mean, the question is, what question are you interested in? Is it extrapolation? Is it parameter estimation? You'll get slightly different answers that all converge, that all are consistent, meaning that with perfect data it converges to the ground truth, but with putting the focus on different points. If, for instance, your data set has outliers that may be artifacts, but you're not sure, I guess putting too much emphasis on them is not a great idea. That's an example.
May I ask a question?
Yeah.
And just a comment, I don't remember the details, but I remember that there was like a relationship between the least square loss function and the maximum likelihood principle. Maybe you remember. But
yeah, maybe I remember.
I've heard that that's some usual motivation also, like people use. And so my question is,
maybe I can answer to this first, yeah, sure. Which is that here we don't have probabilities. There's no likelihood because these are deterministic systems.
But every point, you always have an error, right?
Say again?
You always have uncertainties due to measurements, and every point's got.
Okay, so if you have now, if you add measurement errors, yes, there's a connection. Should I put this? I think if you make a Gaussian model of your measurement error, then minimizing the least square is going to give you the maximum likelihood. Of course, as soon as we introduce stochasticity, everything becomes probabilities, and now that connection will be very important.
Cool. So my question was,
yes.
If you don't measure all the variables, you cannot do this, right?
No.
Okay. So in that case, would you compare like the trajectories that you measure and the integration of your proposed model and try to minimize the square distance between those? Or?
Okay, so the question is about partially observed systems, which are a much harder class of systems. I'm not going to talk too much about that. If you want to hear about how to infer stochastic differential equations with partial observations, the specialist is here. It's João's PhD subject, and he's made great progress towards making this possible, and it wasn't before. So yes, this is going to come online soon. For ordinary differential equations, this is a much older subject. There's papers from the 80s that talk about delay embedding. So essentially what you do is you say, okay, I'm going to augment my data so this is my trajectory. And I know that it's it has some hidden degrees of freedom. And so this is a too low dimensional representation of my system. If I add to my so I want to make a prediction for where I'm going to be on the next point. Based on this is not possible because there's not enough information. There could be so there are hidden states, and just with this one you don't know what the hidden state is, and so you're going to get it wrong. The idea of delay embedding is that I'm going to try to make a prediction on this one based on several previous points. So now if this is for instance, if these are 2D observations, now I don't have a two-dimensional, my function that predicts this point is not a function of 2 parameters, but of 8. And so the information about these hidden parameters is essentially hidden in the way you've varied, your positions have varied over time. And so if you take a sufficient number of delays and space them well, you can reconstruct a hidden dynamics. And there's a theorem that helps you do that, Taken's theorem, that relates the number of delays you need to take to the number or to the dimensionality of the hidden state, and that will help you select how many delays you need in order to represent that. Now that's not going to give you directly a mechanistic model for the hidden variables. That's going to give you a prediction model to fit your dynamics.
Thank you.
I was not really planning to talk about this, but well, yes. More questions?
So the inference error is not the same as the loss function, of course, right? So how should you define
the inference error? Okay, so that's a great question, and that's going to be important. The loss function is something that you can evaluate based on the data only. The inference error is the discrepancy you have between, so I will quite generally call it E, and that's going to be the average of the true force minus the inferred force, and I'm going to take a least square average because mean square average because that's the easiest. So this really, I mean, you do not have access to this with data only. You need to know the ground truth. Yeah. So this is a prediction essentially, and you can obtain this with simulations, but with data only, you don't have access to this curve, so you need to get a method to predict where this point that is just right will be, just with the data. We'll talk about this tomorrow. Yes?
Hi, Pierre. Talking about the loss function, the quadratic function is the best choice. There's an optimal way to find the best loss function. I'm just saying because in training neural networks, we use the cross-correlation. It's terribly better than the quadratic function. It's learn faster, and it maximizes the probability of getting the correct results. So do you know if there's some mathematical way to find the optimum loss function, or you just chose?
So as I said earlier, I will admit not being a specialist of this. It depends what you want. It depends what the goal of the inference is and how you want to penalize discrepancies in your data. I don't know of a general result that will tell you which one you should choose. And right now, I will tell you about a method that uses a different norm in the penalization, actually. And that's going to be Cindy, and let me do this here. sparse identification of nonlinear dynamics. And let me get the reference because I don't have my slides anymore. So it's a paper by Steve Brunton et al. In PNAS 2016. And a near infinite number of follow-up papers since then. I think this paper has more than 4,000 citations. And it's a big thing. I'm going to give you a very, very brief intro to this. What I suggest, if you're interested in this, is to go check the YouTube channel of Steve Brunton. The guy has 400,000 subscribers to his YouTube channel. Amazing videos, very pedagogical in dynamical systems, in neural networks, in fitting, in control theory. I don't know. It's hard to compete. So I'm not even going to try. The idea is that you're going to start with a very large basis. In a linear way, meaning just as before, you do a linear combination of these basis functions. And if your basis is large enough and systematic enough, you can represent dynamics as a linear combination of it. Basically, you can fit any dynamical equation with a linear combination of a sufficient number of functions. And this has to do with, there are mathematical results that back this. And then you're going to perform inference and applying a sparsity penalty, a sparsity enforcing penalty, that will try to get as many of the coefficients to 0. To put as many coefficients to 0. As possible. And I'll tell you briefly about two of these. So now you'll have modified your loss function. Your L is going to be the previous L linear, if you want, plus a second part that will enforce sparsity and that will penalize non-zero coefficients. A simple example of that is to just keep the average mean square discrepancy, so delta x over delta t minus sum over I of the fi of xt, fi bi of xt squared. And here get something that can look, for instance, like alpha, a parameter, times the sum over I of the absolute value of fi. Oh, hey, this is a norm1. This is norm2. This penalty is called lasso for least absolute, okay, I'm having shrinkage selection operator. Everybody calls it lasso. How does it look like? Why is it a good idea? Well, you have, this is your parameter fi, and then your loss function as a function of fi will typically look like a parabola, will look like a parabola actually because, well, it's squared in it. And so if you change a little bit, if you penalize it, adding a square term, you'll just move a little bit the part of the, like you'll move a little bit the minimum. But now if you penalize it, adding an absolute value, so I'm going to add plus alpha times this. Well, if there are two cases. Either it will look like this, sorry, with a minimum that's close to the previous minimum, or if it's too flat around here, it will look like this with a minimum at 0, a sharp minimum. Essentially, this absolute value is going to pin values down at 0. 0 is a stable minimum, and if you add a little bit of noise or change a little bit the data, you'll stay stuck at 0 unless you have enough incentive to deviate from 0. Basically, unless you beat this barrier that is dominated by alpha. This is nice in the sense that there's two really nice things with this approach. It's sparsity enforcing. And it's still a convex problem. All of these curves that I've shown here are convex. There's no concavity of the function. And so numerical solvers like this. There's a unique minimum. What is less nice is that, of course, it's no longer a linear problem. It's not a quadratic function. And so you cannot just write the solution analytically in one go. So that makes it a computationally more intensive method. The second approach that is actually more popular nowadays, even though it was less pushed forward in the initial paper, is called sequential thresholding list squares. And if you try to play with the Cindy package, I actually had a demo, but that I will show tomorrow. I hope everything will be solved. This sequential thresholding list squares basically consists in doing this inference like that, taking the smallest term, so the smallest fi in absolute value, putting it to 0, doing it again and again and again until there are no more terms below the threshold. Kind of naive, works super well. And it's much more efficient. It's much faster than lasso because at each time step you're solving a linear problem, and so you just have to invert a matrix. You don't have to do a minimization. To 0, sorry, and iterate until none is below the threshold. All of this is nice, and I mean, it's already a very broadly applied method. One of the things that I find less nice is the fact that there are hyperparameters. There are parameters that you need to choose, and there's no real prescription for how to do this. You actually need to adjust, adapt, iterate, and it doesn't give you a principled framework to choose how to do that. It's actually hard because in deterministic systems, you don't really know the enemy. The sources of error are not clearly identified. In stochastic systems, well, you're trying to beat the stochasticity. And so it's easier to quantify errors, and we'll see that tomorrow too. I hope I'll get enough time to do everything. Now, before any questions on Cindy? Yes? Okay, so yes, this was a bit artistic. Okay, so this is just a parabola in white. And I add to it this penalty in red that is the absolute value. This is just a triangle. And depending on whether this slope here, so which is a slope alpha, is larger or smaller than the slope at 0 of your parabola, then you'll either, if this slope is smaller, you're not going to get a minimum here. You'll basically slide back to close to the initial minimum. If it's smaller, if you're very flat, basically you don't have a good resolution on your parameter, because changing the value of the parameter does not change much the loss function. You're sloppy, quote unquote. And so if you're sloppy, the lasso will grab you and put you to 0. And that's what happened in this blue curve. Is this a bit more clear?
Yeah, thank you.
More questions?
Sorry. How do you really choose alpha? That's the part of...
Yeah, you basically tune it until you get a number of terms you're happy with. And if you have a big gap in the smaller and in the more significant terms and the less significant terms, then this doesn't matter much, right? But if you have a continuum of terms, less and less significant, for instance, if you're trying to fit an exponential with polynomials, bad idea. But if you're trying to do that, all the terms matter. It's just that they're smaller and smaller. And so where you'll stop will depend on the value of this alpha without a clear prescription on why you should stop. One thing people do to help with this is to normalize first the mean value of the mean squared value of each of the fit functions, so that at least you compare things that have the same dimension. Because here it's not even dimensionally correct, right? If in these bi's you have x and x squared, then the fi's have different dimensions, and you're comparing apples and oranges. You may even, if you're not careful, if you go from micrometers to meters in your data set, you may get a different model. Not very satisfactory.
Yeah, I'm not really sure, but is there a way to select the good FIs that would rely on PCA? An alternative way? I didn't think so much about it, but it seems that it would be a way to select the relevant ones without having to set a threshold.
Well, you still have to put a threshold on your, yes, in your PCA, how many terms do you keep? So I haven't thought deeply about it. But basically, you have your B matrix here that correlates, that gives you the correlates of your variables. And so principal component analysis will detect with if some of these are collinear and will help kill one of them if it's the case. So can't answer that directly, but it's these are very close concepts. Can I get 5 minutes to flash something about neural nets? So I'll just, because this is a broad field and that's opening, I just wanted to mention the existence of physics-informed neural nets. You'll find plenty of good videos and examples, including on the chain of YouTube channel of Steve Brunton. And the reference for that is that's 2000. I think that I don't see it. I think it's 2019. And that's a JCP. C is computational, not chemical. Big field opening. There are beautiful reviews with tens of thousands of citations. It's it's used in imaging. I think it's used in medical sciences. It has not really been used so much for pattern forming systems. But let me give you a very brief idea of how this works. So the idea is that you're going to try to use neural nets to fit your data and the model, fit the data and possibly the model. But you're going to constrain this data, or rather to embed physics law in this data. It's not really a strong constraint. And these physics laws you know in advance. For instance, let me give you very briefly an idea of how this could work for reaction diffusion systems. And there are a few papers that show this on reaction diffusion systems, such as the ones that we've seen the last week. Imagine that you have a field u of xt, u over dt equals d Laplacian u plus a function of u and theta. And you want to know this function of u and theta. You want to know this part that encodes the reactions. But you will make the assumption that your field u, for which you have measurements, u, I, so these are u of ti, x. This field u obeys this reaction diffusion law. So what you're going to do is specify a neural net approximation for u. And so u and n. And so we will define a penalty for this u and n. So the loss, the data loss, is how close your neural net is to the data. So the UNN of, sorry, I'll write it a little bit better. The data loss is going to be a time and space average of the discrepancy between your UI, your data, and UNN of xi t, and that's averaged over I and t squared, of course. Always least squares. So this is going to try to put your neural net prediction as close as possible from the data that you've observed. How to construct that neural net and how this precisely works, I'll let you see in the papers. I'm actually not a specialist of that. Then that would be not so useful if you don't add another constraint, which is that you want to penalize the deviations to the laws of physics you've embedded. And for that, you're going to define a residual, R, which is how much your neural net deviates from this PDE here. And so I'll write it simply, dt UNN minus d Laplacian UNN minus f of UNN theta. So that's a residual that depends on space and time and all the parameters. And now your loss function is the loss on the data plus a sum of the residuals squared. And that's the physics loss. And you're going to run to optimize your neural net, to train it over the values, the nodes of UNN, the values of theta, possibly the value of d here. So this f can be a neural net too, or it can be an interpretable equation, such as reaction rates, for instance. You're going to to train your neural net to minimize this loss function. At the same time, you want to obey the laws of physics and represent the data well. And this actually proves to be much more data efficient than, well, to be very data efficient and powerful. And it's a promising way to estimate parameters and discover dynamical equations from data. And I'm not going to show you anything because we don't have the slides today, but I'll start with showing a few examples on ordinary differential equations and partial differential equations tomorrow morning before moving on to the stochastic case. Thank you. Any questions?
Thanks for the talk. I totally agree that connecting like the biological data to like our like theoretical understanding is somewhat non-trivial and very tricky task. I'm always wondering when I see these approaches, like how much physics comes into the modeling. For the physics-informed neural networks, I totally see that you have lots of ways how to provide input to your model, but how easy is it from these neural networks to then infer like the physical interpretable forms of your reaction terms, for instance? Because like for the other aspects that you mentioned, like Cindy and basically the fitting, I always have trouble to see like how you can turn this into like physically interpretable output and how to connect these two theoretical models.
Broad question. Very fair too. And to be honest, we're not fully there yet. This is an active research direction. Interpretability of all of these equations is a major challenge. Mechanistic understanding is difficult, but we're making progress. So some of the things, maybe some elements of information that I can tell you is, okay, you're not blind. You choose the basis functions that you put in. You can, for instance, force your basis functions to all obey some symmetries. And then take another model where you don't, you allow violation of these symmetries. Compare the two, and that you need to do in a fair way. And then you're asking, you'll know whether there's a significant violation of the symmetries from the data or not. That's physics. You can try to add some terms in your equations. For instance, is this chemical reaction present or not? Is there a direct interaction between these two species, or is there not? And compare between models that have it and don't have it. So these are interpretable terms. And see if they statistically significantly improve the inference, whether it helps or not, and how much. Then another very important aspect is dead data sets are harder to extract mechanisms from than alive ones. What I mean with that is if you're teaming up with an experimentalist who does the data production, you find a model, and you then vary some control parameters in the experiment. See how the parameters of your fitted model or the form of the fitted model changes. Then you try to find a model that recapitulates all that at the same time. That in which, for instance, your control parameter, for instance, let's say the illuminance of your fish school is a control parameter, and if you change that, you learn also the functional response of your inferred forces to that. So having explicitly physically tunable parameters built into your model. That will definitely help with mechanistic understanding. It will provide models that capture a broader spectrum of data with variable parameters. Another example, you have confined geometry and you have cells crawling in this confined geometry. You can try to learn a model for each geometry. Or you can try to parameterize the geometry explicitly, put these parameters into the model as inputs, and then try to find a single model that will recapitulate different geometries and possibly be extrapolated to new geometries that you haven't seen yet. That's also going towards physical understanding. I'm not giving a definite answer to your question. I don't think anyone will today, but there's hope. And I'm not saying that what we're doing here will completely replace modeling or completely replace theory. It will complement it. It's complementing it already. And it's a way to guide yourself towards good models, to guide yourself towards getting the right parameters for these models, and to test hypotheses in a way that is really based on the data and not just on your intuition.
More questions?
Last one. Could you have that alpha is actually a matrix and goes inside that term there with a certain structure? Does it help in any way?
Yeah, it helps a lot. Now, you had one external arbitrarily chosen parameter, and now you have n. N squared, sorry. I think it's easier to normalize your data in a systematic way and then have a single penalty than to expand the number of hyperparameters. Honestly, this doesn't run in a second, right? You need some time to run it if you have a decently sized data set. You don't want to tune each of the many, many different hyperparameters manually. The less you have, the better. Coffee break?
Yep, I think it's a pretty good idea. So we'll start maybe 10 past 11. just pay attention to the bell, because we are going to try to fix the technical issues, and it might be that we need a little bit more of a longer coffee break. But if everything goes ideally, we see you here in 20 minutes, okay? And of course, let's thank Pierre again.